Hi everyone. In this lecture, we'll discuss about the frequency response of a series RLC circuit in a more quantitative fashion than what we did in the previous lectures. So first, we'll write the impedance of a series RLC network, series RLC circuit, which is nothing but the the sum of the individual impedances of the three elements. And I'll substitute S equal to j omega. We have the impedance as a function of frequency. Now this function, it's a complex number, so therefore we'll have both magnitude and the phase. Okay, so before we plot the impedance, so we'll try to see intuitively how does the frequency response and phase response should look like, and then we'll start writing the equations and try to draw it mathematically. So at very low frequencies, when omega tends to 0, you have three elements in series. So the one with the larger impedance is going to dominate. A capacitor is going to behave like an open circuit, inductor is going to behave like a short circuit. So the resistance, the impedance of the resistance, it's constant with all frequencies. The impedance of the capacitor, on the other hand, is going to be infinity at DC and it's going to go to 0 at infinite frequencies. And the impedance of the inductance is actually going to be infinity at higher frequencies and 0 at lower frequencies. And we know that the overall response at low frequencies, the impedance Z of omega is going to behave like a capacitor, because when you have connected, this is capacitor here, this is the inductor, and this is resistor RS. The one with the highest impedance will dominate. So minus j by omega c is the response of this circuit at very low frequencies when omega tending to 0. At very high frequencies, the impedance is going to behave like an inductor here. So that's going to be j omega L when omega tends to infinity. Now from this equation we can see of impedance Z of omega is given by this term. Now this term here, there is one particular frequency when this term actually becomes 0. So that is at omega naught equals 1 by root LC, which is the resonant frequency of the system of the series RLC circuit. It's going to behave like a pure resistor. So the impedance at omega equal to omega naught, it's going to behave like a resistor. So the circuit initially starts off at low frequencies. I'm going to sweep my frequency from 0 to infinity. It starts off to behave like a capacitor. Then at omega equal to omega naught, it transitions to a resistor, and then eventually at high frequencies it transforms completely to a capacitor. Inductor. Okay, at very high frequencies it completely turns into an inductor. So at low frequencies, if you are asked to plot the impedance, so we know that the impedance is infinity. So I'm going to start with omega equal to 0, it's infinity. And again at high frequencies, Z of omega is going to be infinity because it's j omega L. At omega equal to omega naught, the value of this impedance is R. RS. Okay. Now to draw the phase response, we'll just use the fact that at low frequencies it's going to behave like a capacitor, so it is minus j by omega c. So the phase shift, to begin with, the phase shift is going to be minus pi by 2. Okay, I've just taken the phase of this complex number, which is minus pi by 2. And at the resonant frequency omega naught, which is 1 by root LC, the phase shift is 0 because it's purely a resistor. Voltage and current will be in phase, so impedance will have 0 phase shift, 0 phase. So impedance is nothing but the voltage phase divided by the current phase, because both of them are in phase, so you'll have 0 phase for the impedance. And at very high frequencies, when it becomes an inductor, the impedance is actually j omega L, so the phase is going to be plus pi by 2. So this is how intuitively we can draw the response. Now mathematically we can see that mod of Z of omega is simply going to be square root of RS square plus omega L minus omega c the whole square, and the phase of Z of omega, okay, is I'll simply call it phi of omega. It's going to be tan inverse of omega square LC minus 1 by omega c. Now in this term, when I substitute mathematically, when I make omega equal to 0, the numerator becomes minus 1 by 0, it's minus infinity, so phase will be minus pi by 2. And when omega tends to infinity, this function will be plus pi by 2. Okay, tan inverse of infinity is plus pi by 2. And at the resonant frequency, you get 0. Omega equals omega naught as 1 by root LC, you get 0, so you get 0 phase. Okay, so mathematically, again, it's a tangent function, it's arc inverse tangent function, so you can draw it mathematically this way. And the magnitude response, we can see here, this function has a minima at omega equal to 1 by root LC, because the second term, the minimum is you are squaring and adding two terms. So for this function to have the minimum value, the second term has to be 0. First term is always independent of omega, it's always constant. The second term goes to 0 at omega equals 1 by root LC. So therefore that's the minimum value, and the response is shown here at this point. Now in case of a parallel RLC circuit, we saw that the impedance of this parallel RLC network was like this, it was like a band pass response. It had a maximum value, and then it was again reaching 0 as omega tended to infinity. So there the maximum value was Rp, and we defined a term called 3 dB bandwidth. We said that this circuit at the resonant frequency, it behaves like a first order low pass filter with respect to the resonant frequency. Okay, so which means around that the gain starts drooping on either sides. So when I say a first order low pass filter, it's nothing but a filter which responds like this. It's going to start off at a peak value, and then eventually it's going to go to 0. This is shown on a log scale, so a linear line, it will be linear on a log scale. On a linear scale, it will be a response like this. Okay, so we defined a 3 dB bandwidth for a parallel RLC circuit. In a similar way, for a series RLC circuit, the impedance is actually it's just an inverted version of the parallel RLC circuit. So it's going to start off with infinity, and it's going to reach a minimum value, and it's again going to increase. So if I take the admittance of a parallel series RLC network, that's going to look like this function. So similarly, I can define a 3 dB bandwidth for a series RLC circuit as well. So for an admittance, I can define the frequency at which the admittance becomes 1 by root 2 of its maximum value, or for impedance, I am going to define it as the frequency at which the impedance is going to become root 2 of its minimum value. Okay, if I have root 2 for the frequency at which the impedance becomes root 2 of its minimum value. Now we know that the impedance is Rs, which is nothing but root 2 into Rs. So it is Rs into j omega L minus 1 by omega c. So for this to become root 2 Rs, all I need to do is just equate 1 by omega L minus omega c as plus minus R. For both Rs, plus minus Rs. For both these values, this function mod of z of omega is going to be equal to root 2 Rs. So here if you see, for plus Rs, we are going to get one quadratic equation, and when I substitute minus Rs, I am going to get another quadratic equation. So solving the two quadratic equations, I'll have 4 solutions, but out of which I'll discard the negative solutions and I'll retain only the positive solutions, because here we are interested in two frequencies around omega naught where the impedance becomes root 2 of its minimum value. So those two frequencies, I'll call it 1 and 2, or omega naught square. We can very easily show this omega naught by 2q the whole square plus minus omega naught by 2q. Okay, so again omega 1 is, I'm just using the plus term for omega, minus term for omega 1, which is root of omega naught square, and omega 2 is simply this term, or rather now if you look at these two frequencies, if you take the product of the two, omega 1 into omega 2, so this is like a and b, so this is a minus b into a plus b, so you are going to get a square minus b square, so this term is simply omega naught square. So what it tells us is that omega naught is not at the center of omega 1 and omega 2, rather it is spaced geometrically. So rather omega naught is simply the geometric mean of, okay, so this I may not have shown the graph properly, but it goes off to infinity on either sides. Okay, at omega equal to omega naught, it's 1 by rs, and then the two frequencies where the impedance becomes root 2 times its minimum value is actually omega naught, I mean it's actually omega 2 and omega 1, and we said that these two are not equally spaced, but rather they are geometrically spaced. So your omega naught is actually the geometric mean of omega 1 into omega 2. But for very large values of q, you can make an approximation that omega naught by 2q will be much smaller than omega naught. So therefore, your omega 1 comma 2 will be simply reduced to omega naught minus plus. So omega 1 is minus and omega 2 is plus omega naught by 2q. So in that case, your omega naught is omega 1 plus omega 2 by 2. It's now arithmetically, I mean it's like the arithmetic mean of omega 1 and omega 2. In that case, when your q is very large, in that case I can say that the impedance, the frequencies omega 1 and omega 2 are equidistant from omega naught. This is omega 2 and omega 1. So this term omega 2 minus omega 1, which is equal to omega naught by q, this term is called the bandwidth or the 3 dB bandwidth of the circuit. And if you take the ratio of omega naught by the bandwidth, you get q. So q can also be defined from the frequency response plot of a series RL circuit or even a parallel RLC circuit. Now what does q tell you is that if your q is very large, then the impedance graph actually becomes more narrower. So for example, if I plotted for two different values of q, this is for one value of q. If I want to plot the same impedance, I'm keeping r constant, but say somehow the q is large, then the graph is going to look something like this. It's going to become more narrower. So q tells you about the narrowness of this the frequency response of a series RLC circuit. And similarly, even for a parallel RLC circuit, larger q would imply a narrower response. Okay, so this is other definition of q, which we didn't mention in the last lecture, but this is from the frequency response. You can actually guess the q from a frequency response of a series RLC circuit as well. Okay, now I'll try to give another intuitive explanation for, let me just quickly summarize what I discussed right now. So we analyzed the series RLC circuit at three different frequencies, and omega equal to omega naught and omega equals infinity. So here I said that at low frequency, that omega equal to 0, it behaved like a capacitor. At resonant frequency, it behaved like a resistor, and at infinite frequencies, at very high frequencies, it behaves like an inductor. This is RS. Okay, we said the series RLC circuit, the behavior of series RLC circuit, we analyzed it at three different frequencies. Now we'll try to understand what happens in terms of circuits. Can we actually try to capture a model for this series RLC circuit near the resonant frequency? So when your omega is very close to omega naught. So we are interested in frequencies which are at omega plus minus delta omega. So the series RLC circuit, the impedance is given by Rs plus j omega L minus 1 by omega C. Okay. So here I am going to substitute omega as omega plus minus delta omega. Okay. Or let me just first write it for, I'll write it as plus minus delta omega and substitute it in this. this can be reduced to j omega square LC minus 1 by omega c. I'll substitute omega as omega plus minus delta omega, and I'm going to get a term like this. So if I take omega naught common out, so you'll be left with omega naught square LC into 1 plus minus delta omega by omega naught the whole square divided by omega naught c. Okay, this term, it has omega naught plus minus delta omega, but since delta omega is much smaller than omega naught, I'll ignore delta omega there. So this term, you'll be left with omega naught L into 1 plus, there is also a minus 1 in the numerator. There is also a minus 1. So this term omega naught square LC is 1. So this term, I'll just replace this term as 1. So you will actually get, again here I'm going to use, I'm going to ignore the delta omega square term, delta omega by omega naught the whole square, I'm going to ignore that term. So we can write this as Rs plus j into 1 by omega naught c plus minus delta omega by omega naught. Okay, 2, there is a factor 2 here, plus minus 2 delta omega by omega naught. So since we know omega naught c, 1 by omega naught c is omega naught L, so I'll write it as Js plus minus j delta omega. I will replace this term with by omega naught L, and omega naught would cancel out. You will be left with delta omega into 2L. So if you look at this, this is nothing but a resistor and an inductor in series. Okay, of value, inductor of value 2L in series. So for example, if I were to plot the frequency response of this circuit of simply a resistor and inductor in series, then this circuit, we know that this is impedance is Rs plus 1 by 2SL, Rs plus 2SL. So this circuit has just one 0. So if I plot the impedance at low frequencies, it is Rs, and then it's going to blow up to infinity as you keep increasing the frequency on either side. This is for negative frequencies. Okay, this is for omega less than 0 and omega greater than 0. This is for, okay, and at low frequencies it's going to be Rs, the impedance at this point, and we are interested at 0, which is at Rs by 2L at that frequency, and minus Rs by 2L. The impedance is going to be root 2 Rs. Now if I replace this entire circuit, if I just shift, if I just shift this whole function and then place it at omega naught. Okay, if I place it at omega naught, you would see a very similar behavior. Okay, so this circuit, so essentially a series RLC circuit at omega naught is going to behave like a series RL circuit with an inductor of value 2L, and this approximation is valid for frequencies very close to omega naught. So your delta omega is much smaller than omega naught. So around omega naught it's going to behave like a resistor and inductor of value 2L in series, and the 0 of that impedance is given by omega naught. Here it is plus delta omega, which is plus Rs by 2L, and we can very easily show that. We just mathematically just derive that result to be omega naught plus omega naught plus omega naught by 2q. Now if I substitute q as omega naught L by Rs, if I substitute q here in this equation, I am going to get omega naught plus Rs by 2L. Okay, so that's the 0 of a resistor of value Rs and 2L in series with it. In the same way, we can also show that, we have already done that. I'm just trying to reiterate it again here. For a parallel RLC circuit, so if I have a parallel RLC circuit, we know that the impedance at the resonant frequency, it's going to behave like it's going to behave like a low pass filter, at the resonant frequency. The model for this at the resonant frequency and for frequencies very close to the resonant frequency, or for frequencies very close to the resonant frequencies, omega plus minus delta omega, this circuit will behave like a resistor and capacitor of value 2C in parallel. Again, this can be very easily shown. If I take the admittance of this network, it will be 1 by RC plus J into omega C minus 1 by omega L. From that, we can very easily show that this will reduce to 1 by RP plus minus, this is omega L, plus minus J into delta omega into 2C. Okay, so we can very easily show that it reduces to this. So which means this looks like a frequency translated response of a parallel RC circuit. The impedance, the frequency response of a parallel RLC circuit looks like a frequency translated version of the impedance of a parallel RC circuit of value RP and 2C. So I just plot this impedance for low frequencies and then frequency translated to the resonant frequency. It will be the same. And the 3 dB bandwidth here, it's going to be 1 by RP, 2 RP into C. Okay, again you can very easily show that omega naught by 2Q for a series for a parallel RLC circuit, where Q is, I'm going to write Q as omega naught RP into C. So this will reduce to 1 by 2 RP into C. Okay. So just to summarize, we try to analyze what happens for a series and a parallel RLC circuit near the resonant frequency. A series RLC circuit, a series RLC circuit behaves like a resistor connected in series with an inductance of value 2L. Okay, this is for frequencies closer to the resonant frequency. Its impedance is going to increase to infinity in either directions, but near the resonant frequency it's going to behave like this. And the point where the 3 dB bandwidth occurs, this is true for large values of Q, omega naught plus Rs by 2L and omega naught minus Rs by 2L, which is nothing but omega naught by 2Q. Okay, and similarly we said for a parallel RLC circuit, the circuit is going to behave like a parallel RC circuit for frequencies very close to the resonant frequency. The impedance is going to drop on either sides of the resonant frequency. Here the value is 2C. Okay, the peak value is RP. It's going to drop to RP by root 2 at omega naught plus 1 by 2 RPC. Okay, and omega naught minus as well. Okay, so this is it. I wanted to discuss about a series RLC circuit in a more quantitative fashion. What happens to the frequency response at low frequencies, high frequencies, at the resonant frequency, and frequencies in the vicinity of the resonant frequency. We analyzed it for all these frequencies. In the next lecture, I'll try to generalize these results and present it for a generalized bandpass transfer function. Okay, the results that we derived for a series RLC circuit near the resonant frequency. So we derive similar results and some more interesting results for a bandpass response in the next lecture.